So you remember when we talk about that, that example for the, can you see any chalk? Okay. Sabotage. Okay, here. Chalk. Remember when we talk about the temperature in your cabin in the woods, right, in the mountains, right? So what we said is that, okay, so let's say that the temperature outside is 0 degrees, so you have left, you've been away from your cabin for several months, you walk into the door, the temperature will be 0 degrees, right? So then what you would like to have is, say, a temperature of, say, 20 degrees or whatever you like, right? What do? Right? So let's say that so you have this heater, right? And then, the heater has a bunch of different settings, right? Let's say, goes from, say, 1 star, 2 stars, 3 stars, all the way to 5 stars, okay? Maybe you know that, at the steady state, what you like is 3 stars, right? So one of the things that you can do is, set the control to, set the heater to, say, 3 stars, right? And then we know that the temperature will eventually approach the temperature, the equilibrium temperature, okay? And let's say that this time here is, say, 3 hours. Okay, so this is time, and this is temperature, okay? Okay, so do you really want to wait 3 hours? So you just got into the cabin, right? And, you want to get comfortable, right? So would you want to wait 3 hours? Maybe not, right? So what is it that you would do? Right, your options, okay, your control input can be, say, one of, either this 1 star or 2 stars, okay, 3 stars, 4 stars, or 5, right? Whatever, okay? So what would you do? It's freezing cold, so the first thing that you would do, I imagine, is, what would you set it there? Anybody? Freezing cold probably would max out. You would set it to 5, right? What would happen if you set it to 5? Right. So probably what we will do is, maybe we'll go to, I don't know, like a 40 degrees or something, right? So probably this would be something like, something like that, right? So this would be for 5 stars, okay? And this would be for 3 stars, okay? But then what would you do? So what you see here is that, what do you think is the shape of these two curves? How is the shape of these two curves related to one another, assuming that the system is linear? Something you may notice is that the time constant of the system is still the same, okay? However, since you are aiming at the target that is higher, you will actually get to 20 degrees much faster, right? Is that all you do, right? So you set this thing to 5 and then enjoy the, the warmth? Well, probably, pretty soon you will start sweating, right? So what is it that you would do at that point? Anybody? I see you smiling, so you have something in mind, right? So, yeah.
When it gets to 20 degrees, I would set it to maybe 1
Okay. So you're saying that, when it gets here, what you will do is set it to 1. Okay. If you set it to 1, what do you think will happen? So this is the equilibrium temperature for 3. So maybe the equilibrium temperature for 1 will be somewhere here, right? So if you set it to 1 here, it will probably start decreasing again, right? One of the things that you could do is, well, for example, if you know that if you wait until it hits 20, then when it gets to 20, you can set it to 3, and then you will know that it will stay. This is the equilibrium temperature, right? But you're also burning a lot of energy, right? By, when it's set to 5, it's burning a lot of energy. So something else that you could do is, well, when it got kind of like a halfway through, or it's getting close to being comfortable, what would you do? Maybe you don't keep it at 5. Maybe now you reduce it to 4, right? Okay. So then, so essentially what you can do is, up to this point, you use u equal 5, right? So then maybe at some point here you set u is equal 4, right? And then when it gets here, you will set u is equal to 3, right? Now, how do you set these points where you set when you change the setting on the heater? By feedback, right? So essentially, you walk into the house, the cabin, it's very cold, so you set the heater to a very large value, right? As the temperature rises and your degree of uncomfortable, I mean, you feel less and less cold, then you start reducing the setting on the heater, right? And this is exactly the concept of feedback, okay? Now, let's see what do you remember what the equations will look like here? So this is a first order system, right? So what we can say is, okay, so x dot will be equal to some minus a x, right? Plus some b times my control u, and then y will be equal to, say, some cx, okay? What is A in this case? We said that the time constant here, if you just draw this tangent and look at when it intersects the asymptote, the intersection happens at 3 hours, right? You remember how the time constant is related to the A coefficient or related to the eigenvalue? No? No way? You can think of it. What is the derivative at this point? The derivative at this point is exactly A, right? Assuming that, let's say that C is equal to 1. The derivative at this point is exactly A, right? Okay, so, and the derivative will be, it's 1/3, right? So, because essentially you will get all the way to the equilibrium point, right? You divide by 3, right? So, we can say that this is minus 1/3, right? Where the units of time are hours, right? So 1/3 hours, okay? Okay, now when you apply a stronger input, right? So if you use 3 or if you use 5, what happens? This time constant does not change, right? Only the equilibrium value will change. So you see that if this is, say, 40 degrees, you will still reach 40 degrees with the same time profile, right? So with the same time constant, okay? The fact that the temperature increases faster is because you're multiplying everything, right? So you see that the time constant here is 3 hours, the time constant here is 3 hours, okay? But by doing this feedback, what happens actually is that by setting this to 5, so you get the temperature to rise quickly, then you set the temperature to 4, right? and then you set it to 3, and essentially what you will get is something that is like that, okay? So essentially what you see is that the shape of your response is actually changing, okay? Not only the scale, okay? What do you think happens to your time constant? The time constant is what you get by drawing this and looking at where it intersects your steady state value, right? So you see that the time constant now is much reduced. It's much smaller, okay? So what does it mean in terms of your system equations? Now let's say that this is now is, okay, so this is say 1.5 hours, right? So then what happened to your time constant? Went from 1/3 to 1/1.5. Okay, so the time constant gets smaller. The time constant gets smaller, meaning that your A coefficient, in a sense, gets larger. Okay. Okay. So if you had to draw this on this complex plane, the pole zero map, right? What you have is that your system has a pole here, right? What is the transfer function of this? How do you compute the transfer function here? This would be 1 that multiplies S plus 1/3 times B, right? For whatever value of B, okay? This is inverse, okay? So what are the poles of this system? It's negative 1/3, right? Yeah. Okay, now when I apply my feedback, what is happening? So let's say that my feedback is that U now is minus K times the temperature, okay? Okay, so let me write it this, okay? Minus K times Y minus your reference, your desired temperature, okay? Meaning that if the temperature is too large, then you reduce your heating, okay? If the temperature is too low, then you want to increase your heating, right? Just look at the, and then what the equations will become, right? So what you will have here is that now X dot is equal to minus 1/3 X minus B multiplies K. You know that Y is equal to X, okay? Plus BK some X reference, okay? So what happens to the pole, to the eigenvalue in this new system? You see that essentially this is the same as having the new system, which has minus 1/3 plus BK X plus BK X reference, okay? So in a sense, this X reference has become your new input, right? But what has happened to the eigenvalue of your system? It was minus 1/3 before. If you keep K is equal to 0, remains at negative 1/3. But if you make K larger and larger, what happens to this eigenvalue? Becomes more and more negative, right? Okay? So essentially, as you increase K, your eigenvalue, this will be the closed loop eigenvalue, right? So this will be the eigenvalue of your closed loop system, will move to the left, right? What does it mean in practice? The response here was something like, for example, the step response was something like that, right? With kind of, we know that this would have been, 3 hours. The time constant was 3 hours, right? If I move the pole to the left, what it means is that I still have exponentials, right? But the exponential will be faster. Okay? Okay? You see what is happening? Essentially, by feedback, you can change the dynamics of your system, okay? Your closed loop system, that is your system under the effect of your feedback control, will have a different dynamics. In this case, the dynamics of your cabin open loop was too slow, right? It takes 3 hours to warm up. By feedback, we can make it faster, okay? Let's see if we have better luck now. Any questions on this? So I'm just trying to figure out how to open this in another application. Stupid. Do you know if we can use this tablet? No? Okay, I'm restarting the thing, so hopefully better luck. Yeah. Yeah, but actually, just today, actually what I wanted to do is a lot of drawing on the tablet. So, if you don't mind. Okay. Thank you. Want to put it here? I don't want that to fall. Okay. And how do I actually write?
On the pen, and here you can change the colors. It's like
Perfect.
red,
Okay.
green,
Perfect. Perfect.
different sizes you can
Okay.
see.
And here is okay. And then we need to connect it.
HDMI.
HDMI.
On the other side.
Where is it?
The other way around. Yeah.
Okay. We'll see something. Okay, but then maybe we'll turn around over the.
We'll stay there.
You say that?
So,
Okay.
Because it's better if you touch this.
Okay. Okay. Perfect. Perfect. Thank you very much. It's a community effort. Really appreciate your help. Yep. is U, right? So U is changing, right? Of course, in linear systems, so when I say 1 to 5 stars, that's what you typically have on these heaters kind of things. And that's one of those values. In linear system, we need to have a continuously changing control input, right? So it's kind of an approximation, okay? The idea is that, the colder you are, the higher the setting on your heater, right? Probably, right? And then as the temperature gets closer to what you like, you will probably turn it down, right? Okay? When the temperature is exactly what you like, you don't touch it. Okay? Okay? Okay, so let's get back to the, to the lecture today. Okay, so essentially we are at this point here. Okay, here this is just writing. Can I just highlight? Can I just, have like a pointer? Is there one of these? Maybe I can.
I think we don't have a pointer tool like with the pen. I think if you want to point.
Okay, I need to use on the mouse. Okay.
There is a button on the.
Okay. Sorry. Anyway, so we are at this point where, actually what we start doing today, we will start looking at what is, so essentially we have completed the part on the analysis of systems, okay? So now, if given a system, you have an idea of how, thank you, of how you can come up with a model, right? Get the equations that describe the behavior of the system. Then, given these equations, we know what we can expect. We understand how the system will behave, okay? We know that if these poles that are the eigenvalues of the A matrix or the poles, the roots at the denominator of the transfer function, have negative real part, the system will be stable. If they're complex conjugate, the real part will be how quickly they decay. The imaginary part will be how fast they oscillate, right? Okay, so on and so forth. Now what we want to do is, okay, so now we have a system, we can model it, we know how it works. Chances are that it will not work in a way that you like. Maybe it is unstable, maybe it is too slow, or maybe it oscillates too much. So now what we want to understand is how to change the behavior of this system by using feedback. And this is exactly what we start doing today, okay? So first of all, we will look at what are the standard feedback control configurations, sorry for that typo, and some of these transfer function nomenclatures. We talk about a number of more like technical concerns, like something called well-postedness. Essentially, we want to make sure that our feedback interconnection is actually something that makes sense, okay, from the physical and mathematical point of view. We'll touch on something called internal stability versus input-output stability, and then we start looking at what is really my favorite method. Okay, so this method is just so much fun to use. And this is something that doesn't require any calculations at all. All you need is a piece of paper and a pen, and really gives you a lot of insight on what happens when you apply feedback, and also gives you a lot of insight on what kind of feedback designs will actually be useful, okay? And these are all pencil and paper or tablet and stylus, okay? Depending on what you like to use, okay? So let's get started. Right. So, okay, so this is just philosophy, essentially what we just said. So we know how to model the system. The system, we may not like it, so now we want to change it by feedback control. The methods that so we will discuss a number of methods that kind of like a double both as an analysis tool that allows you to understand what will happen, how will the closed loop behave given a certain control design, but you can understand that if I can see how the closed loop will behave given a control design, this is also something that allows me to choose between different controls, okay? And essentially, have some indication of what would be a good design for my feedback control, okay? Okay, so what is the standard like a feedback configuration. Okay, so essentially here what we have is, okay, so I don't know if, well, the thing at the top, okay. So we had the plant, okay. So remember that for whatever reason, the system that you want to control is usually in control systems called the plant, okay. So we indicated the transfer function is P of S, okay. Now what we are doing now is we're taking the output of this plant, comparing it to a reference that you see on the left-hand side, this R, right? The difference between what you would like to have, that is the reference, and what you actually measure from the plant, that is Y, is your error, okay? Your error E. Then from this error, you put that into some control system, right? So this will be your feedback control system. And your feedback control system, depending on the error, will generate the input that you provide to your plant, okay? Now, and you start seeing why these transfer function things are actually useful. Because now what you see is that, if I can write it here. If I know that, say, U is equal to, U is equal to e to the power st, right? This is our exponential input, our test input, right? So then what I know is that Y will be some P of S times e to the power st. This is assuming, this is the steady state, and this assumes that P of S is actually stable. Remember that, okay? This is only valid in the case in which your system is stable, okay? But then, let's say that R is equal to 0, then what you know is that what would be E, where this is the error, is not the, the basis of the natural logarithms, right? So E will be equal to, well, this will be equal to just minus Y, which is equal to minus P of S times e power st, right? What will be U? Actually, let me write it as this R, okay. So U will be equal to U must be equal to C of S. Let me erase this R, okay? Sorry for the confusion. So U will be C of S times P of S e to the power st, okay? So essentially what you see here is that you can just multiply the transfer functions of blocks that are next to one another. Oops. We can bring back the slide. Thank you. Okay. Imagine doing that with state space matrices, right? State space models, right? So you will have humongous matrices. You will have to assemble them in a complicated way. You don't want to do that, right? On the other hand, if you just use transfer function, it's just multiplication of transfer functions. Okay? Easy. Okay, so nomenclature. So what you see, so imagine that you cut the feedback loop, okay? So you just cut the return path, okay? So then what you will have is just a series of two blocks, right, going from R to Y, okay? That is what is called the forward path, okay? The product of all the transfer functions on the forward path is what is called the loop gain, okay? So essentially this is the open loop transfer function, okay? So this is, if you didn't have that feedback path, okay, this would be how your system will behave, okay? Now, then on top of that, you can compute the closed loop transfer function from R to Y, okay? So this is the transfer function, that relates my output Y to my new input R, which is my reference input. So this is now what I the temperature setting of my thermostat, the speed setting of my cruise control, so on and so forth, okay? You can do your algebra, and what you will find is that this transfer function is actually given by L of S, where L is the loop gain, divided by 1 plus L of S, okay? If you remember, we did this calculation probably on the very first lecture, okay? There is another, and this function is also called the complementary sensitivity, okay, for whatever reason. I think of this is the closed loop transfer function, period, okay? If you want to sound cool and, if you want to impress people that you're an expert in control theory, you call it the complementary sensitivity thing, okay, transfer function. The sensitivity function is the transfer function, again, in closed loop, from your reference to the error, okay? This is called the sensitivity, yeah?
What exactly is the reference?
This is again, this is your this is what you would like the output to be, okay, for whatever the output is, right? So you're thinking about temperature control, your output is temperature, your reference would be your desired temperature, okay? Okay? Your control system is a cruise control in your car, your output is the speed, your reference will be the desired speed, the speed at which you want to go, okay? Okay? Okay. And then so we're saying this transfer function from the reference to the error is called the sensitivity function. Now, you may understand why the other function is called complementary sensitivity, because if you add sensitivity plus complementary sensitivity, what do you get? One, yeah, okay? So, people like to define this sensitivity transfer function for whatever reasons, and then the other transfer function, which I actually think is the meaningful one, is 1 minus the sensitivity. That's why it's called the complementary sensitivity. It's the complement to 1 of the sensitivity function. Don't ask me why people came up with these things. I mean, was 56 years ago, okay? And I don't know what they had in mind, but this is this is the the standard nomenclature. Yeah, questions? Oh, sorry.
First, in this sense, what exactly is enclosed in the open loop, and why do you differentiate between the two?
No, is.
How do you derive these equations, or how do you?
Right. Okay. So. Closed loop versus open loop is not a part of the system. You cannot say that this is the closed loop part and this is the open loop part. Open or closed loop is something that you say about the whole architecture, right? The fact that it's closed loop is driven by the fact that you have this feedback, right? You have this feedback loop.
But in this case, you can define both the open and closed loop.
But yeah, it's not this case. So when we talk about the this loop gain, is what you will get if you imagined a different system where you don't have the feedback connection.
Like a feed-forward system.
Just a feed-forward system only, right? Okay, but you cannot say that this thing has an open loop part and a closed loop part. The whole system is closed loop or open loop.
So looking at the loop gain, we only look at the.
So when you look at the loop gain, yeah, you just multiply all the transfer functions, okay, in your loop, but you assume that you cut the feedback. Okay? So that would be the transfer function that you would have if you had no feedback. But it will be a different system. Think of this loop gain as a mathematical construct in a sense, right? So it's just the product of all the transfer functions, which, by the way, would be the transfer function of a hypothetical system where you had no feedback. Okay? Okay, so we can do the calculations. We did them, on the very first lecture, right? But let's do them again, right? So essentially, what we have here is that y okay, let's just say that R is equal to some let's say, okay, so R is some, say, R bar times EST, okay? Then what we know is that, yeah, can we keep maybe the slide as well, so that, use it, okay. So then we have that, okay, so then Y is equal to, okay. So E will be equal to R minus Y, okay? U will be equal to, let me just write it as this, okay? So we know that everything will be something multiplied by e to the power st, okay? U will be equal to C of S times E, which is equal to R minus Y e to power st. We know that Y will be equal to P of S times R bar minus Y bar e to the power st, right? Okay, so I'm just doing the algebra, right? Oh, sorry, I forgot here there should have been a C of S, okay? Now, P of S times C of S is what we call the loop transfer function. So this is actually L of S, right? So this is actually equal to L of S times R bar minus Y bar e to the power st, okay? So then, okay, so then we can go back here, right? And then what we have is, so I got a little bit confused here. So I'm getting a little bit confused on the steps, on the next steps. Oh, yeah, okay. But we know that this must be equal to Y e power st. Okay, sorry about that, I got lost a little bit, right? So we know that this must be equal to this, right? So essentially what we can write is that L of S times R minus Y bar is equal to Y bar, okay? So from that, what we can, now we can solve for essentially Y bar. So we can write this as L of S that multiplies 1 plus Y bar. No, sorry. There is a, so this is 1 plus L of S, then multiplies Y bar is equal to L of S R bar, right? Which means that Y bar is equal to L of S over 1 plus L of S R bar, okay? And you see that this is exactly the transfer function from R to Y, okay? Okay, good. Sorry about the confusion. I was not planning to do this, and this is a calculation that we did first day of class. Okay, so just a refresher. Sure, no problem. Okay, now the very first thing that we had to mention, not because it's terrible. I mean, this is one of the things that mathematicians worry about. But if you try to do a number of things in MATLAB, MATLAB can start throwing errors at you, okay? So at least you can understand why MATLAB is getting upset. Now, imagine that we have just static gains, okay? So now both D1 and D2 are just some constant that multiply the input, okay? Now, you can do your calculations, try to compute the transfer function, right? And at the denominator of the transfer function, what you will have is 1 plus L, which is equal to 1 plus the product of D1 and D2, right? Now, you can imagine what will happen if D1 times D2 was actually equal to negative 1. You get in trouble, right? You get like a red mark on your, on your homework, on your exam, and MATLAB gets upset, right? Because now this is something that doesn't make mathematical sense. And if it doesn't make mathematical sense, chances are it doesn't make physical sense. Yep.
Are those T1 and T2 in any way related to the D from the stable space?
That would be exactly the D, yeah. So if these are static gains, then D1 and D2 will be exactly the D matrices for those two systems, and the A, B, C will actually be the empty matrices. It will just not be anything. Okay, so this will be exactly the D terms. Okay. Okay. So you just have to be a little bit careful. If this product of D1 and D2 is equal to -1, then your system is not, what is called is not well posed, in the sense that it doesn't make mathematical sense, because you will have as the denominator of this transfer function, you will have something that goes to 0. And as we know, you cannot have a fraction with the denominator that goes to 0, okay? Actually, that is exactly 0. Okay, in general, let me just conclude the thought here is just never put in feedback blocks which have non-zero fit through, okay, because then you can get into these well-posed issues. MATLAB will get upset at you. We start talking about something, MATLAB calls things of these as algebraic loops, okay? So just don't do it, okay? Just make sure that you never have a product of, terms, feedback of terms with non-zero fit through, okay? And also in some condition can make the system ill-posed. Okay, let's take a break here and then we'll continue after the break. Okay.
That you once spoke about with the little ducky?
Yeah, you will see. You will type.
Come, or?
Thinking about mid-November, hopefully. Sorry about that. Okay, let's keep going. Hey. You can have your computer back. I reset the iPad and now it's working. Okay, thank you very much. Okay, so another thing is that, something I have to be a little bit careful about is that, it is tempting to just check that the interconnection is input-output stable, meaning that the transfer function from the reference to the output has no poles with positive real part, okay? However, just look at this example. Let's say that I have my plant is a transfer function s minus 1 over s plus 1. Let's say that I choose my control system to be 1 over s minus 1, right? So then what I would think of is that, okay, so I compute the closed loop transfer function. It is 1 over s plus 2, okay? So then it looks like the eigenvalue, the pole of this is -2, negative real part, everything seems to be okay. However, if you compute the transfer function from R to U, that is your, it's the product of these two transfer functions, what you see is that what you have is one unstable pole. Okay? What is happening in this case? What is happening is that at your output, everything seems okay. However, your controller is melting down, right? So it's kind of like is going to infinity or something like that, okay? That's something that you do not see at the output, so you think you're okay, but you're not okay. Okay, and see what happens here. So essentially what we did here is, for whatever stupid reason, The plan has a no minimum phase 0. And somebody who thought to be clever say, oh, okay, we don't like no minimum phase zeros, so let's put this pole that cancels that 0, but it's an unstable pole. Stupid idea, okay? Because, yeah, now your input-output looks great, but your controller is exploding, okay? What is happening here is actually, if you go back to what we were talking about, the controllability, observability, is that now you have an unstable mode that you have made unobservable, okay? So now your system is blowing up, you just don't see it at the output, okay? But doesn't mean that it doesn't blow up, okay? So in general, again, never, ever cancel an unstable pole with a 0. Just don't do it. Don't, okay? And I guarantee you that somebody will do it, okay? But, okay, so just don't do that, okay? And really, technically, what you will have to do is to check that the system is not only input-output stable, but is internally stable, is check that all transfer functions between any two signals in your interconnection are actually stable transfer function, meaning that the poles have negative real part, okay? But in general, this only happens when you do something stupid like trying to cancel an unstable pole with a 0. So don't do it, and you're fine. Okay, so, yep.
Could you explain on the previous slide, picture number 1, what exactly is happening with non-zero feed-through? What does that mean?
The feed-through term is, in the state space model, is your D term. So feed-through means that, if you remember Y, the output is equal to C times X plus D times U, right? So if D is non-zero, the output you see the output directly at the output. You see the input directly at the output, right? So this is what feed-through means. So if D is 0, then what it means is that now the input does not affect the output directly, only through its action on the state. Okay? So then what you want to make MATLAB happy, for example, is that you want, in your feedback loop, you want to have at least one block that has a 0 feed-through. At least one. Okay? Okay? Do not have feed-through in all the terms. MATLAB will tell you. MATLAB gets upset. And in particular, if the product of all these D terms equals -1, they actually even more trouble because your mathematics just do not make sense. So again, just don't do it. Typically, this is only something that happens in exams and homework and things like that, or something that you just cook up as a simple example, because any physical system will not have a feed-through, right? Any physical system that is non-trivial will have some dynamics, meaning that you will not see the output directly, okay? This is more of a technical, this is what things that mathematicians worry about. The reason why it is important for you to know is that sometimes, I guarantee you that will happen in your life, you will start getting all these errors in MATLAB, and you want to understand why you're getting the error, okay? Okay, so now, what we know is that we have an open loop system, we don't like it, we want to design some feedback control, and we want to change, so that the closed loop will be something that we like, okay? So how do we determine what the closed loop behavior will be? Well, something that you can do is just go to MATLAB, rewrite the equations, compute what will be the new eigenvalues, what will be the new transfer function, what will be the poles of the new transfer function, which is the same thing, right? And then check if you like it or not, okay? Two problems. Now, in this case, you're doing way too many calculations. Second, you have no guideline on what will be good choice of your controller, right? Because if you just take a controller and see if it works, trial and error, yeah, okay, you can do that, right? But you don't have, if it doesn't work, you don't have a good sense of what to try next, okay? So what we do in this class, and that essentially is the the whole point of classical control system, which is what we cover in this class, is to learn as much as we can about the closed loop behavior, just knowing the open loop behavior and doing as little calculations as possible. These are techniques that were invented in the 50s, 40s, 50s. They didn't have computers, or if they had computers, were like as big as this room, right? They were very expensive to run, right? So they were doing a lot of calculations just by hand, using paper and pencil, maybe some slide rules and things like that, okay? And this is exactly what we are doing, in the remainder of the class. We will actually look at three methods. Okay, so the root locus method is the first one. Really like it a lot. I find it, a lot of fun. Really, something that allows you to do a quick assessment of control design feasibility. The results that you get are always correct and are actually very clear, at least to me. Okay, I hope they will become clear to you as well. You can only use it for finite dimensional systems. Essentially systems that we can write as a transfer function with poles and zeros. It's not really something that you use to do sophisticated design, okay? And also it's hard to represent uncertainty. But I think that, these are, okay. These are some of the disadvantages. In the future weeks, we will cover other techniques, something called the Nyquist plot, something called the body plot, but we'll discuss pros and cons as we get there, okay? Okay, so let's get started with this root locus method. So again, something was invented in the late 40s. Okay, so these were people were trying to, the 40s had like a World War II, right? And people were designing, for example, ships with guns, right? And then you wanted to keep the gun pointed in the right direction, even if the ship was rolling, right, in the ocean, or maybe a gun on a tank. And again, you wanted to keep the gun pointed in the right direction as the tank maybe was moving. Okay. Just like wars typically give a good boost to a lot of these engineering techniques, okay? Essentially, this is where a lot of these things came from. Okay, so now what we want to do is really want to understand how the roots of a polynomial, in our case, the roots of the denominator, that is the poles of the system, change as a function of some scalar parameter, in our case, the gain, okay? So in this setup, what we assume is that, okay, so now we have my loop transfer function, okay? This is my open loop system. And I put it in feedback with just a gain k, okay? And then I close the loop. So the loop gain is something that we can write in this way, okay? So it's just k times L of s. Let's write in this what we call the root locus form. We will see why, essentially to use it, to make it convenient to use using this technique. And remember, the root locus form is something where we factorize all the polynomial denominator, factorize the polynomial denominator, and choose a constant, in front of the fraction in such a way that all the coefficients of the s terms are equal to 1, okay? Sensitivity function would be 1 over 1 plus KL in this case, okay? So you see that the closed loop denominator will be given by d of s plus k times n of s, okay? And the closed loop poles will actually be the roots of d of s plus kn of s, okay? So now what we would like to do is understand what happens to the closed loop poles, that is, what happens to the closed loop behavior as we change k, okay? So how do we start? Well, the degree of d of s plus k n of s, so the degree of the closed loop denominator, is the same as the degree of d of s, right? Because we know that the numerator cannot have a higher degree than d, right? So essentially meaning that the number of poles in the closed loop is exactly the same as the number of poles in the open loop, okay? Under feedback, you can change the location of the poles, you cannot change the number of the poles, okay? Now, as you can imagine, if k were to be equal to 0, your closed loop transfer function, your closed loop denominator would be d, which is exactly the same as your open loop denominator. So what does that mean? When k is equal to 0, your closed loop poles are actually the very same as the open loop poles, which is kind of obvious, right? So if your feedback gain is 0, then you're essentially not applying any feedback. So the closed loop is exactly the same as the open loop, okay? Well, I mean, that's kind of not surprising, okay? The other thing that happens is, now let's do the opposite. Now let's say that instead of using a very small gain or a 0 gain, we use a very large gain, okay? So in the case in which the degree of n of s is the same as the degree of d of s, that is, the number of zeros in your transfer function is exactly the same as the number of poles in your transfer function, then when k is very large, what you see is that this polynomial here can be approximated just by your numerator, right? So essentially what we know is that as you increase your gain k, when k is 0, the closed loop poles are the same as the open loop poles. As you increase k, the closed loop poles will actually approach the open loop zeros. We'll do a lot of examples, okay? If you don't have enough zeros, that is, if the degree of n is less than the degree of d, then what you would have is that these excess poles will actually go to infinity, and in a way that, again, we will see in a few minutes, okay? Also keep in mind that the closed loop poles, no matter what you do, remember that everything must be symmetric with respect to the real axis, okay? So if you have a pole that is closed loop pole that is complex, which has a non-zero imaginary part, you also need to have the complex conjugate. Yeah.
Simple question. What actually is n of s?
N of s is the numerator of the transfer function. Okay? Remember, this is how we write the transfer function, right? Okay? So these are the rules, okay? So we'll go through a number of rules and we'll do examples. So you can also rewrite that characteristic equation just by rearranging these polynomials in this way, okay? So now what we have is that the ratio of numerator over denominator must be equal to -1 over k, okay? This is the same as before, okay? Just a different way of writing this equation. Now, if I take the argument, so this is a complex number, this is another complex number, right? So what I can do is I can take the argument of the numerator. The argument of the numerator will be the sum of all the arguments of the factors, right? So this will be the argument of s minus z1 plus the argument of s minus z2, blah, 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 plus the argument of s minus z sub m, okay? Minus, then I had to subtract the argument of all the terms at the denominator, okay? And so this will be the argument on the left-hand side. What is the argument on the right-hand side? If k is positive, -1 over k will be a negative number. What is the argument of a negative number? Is 180 degrees, okay? If k is negative, then -1 over k will be a positive number. What is the argument of a positive number? Is 0, okay? Of course, you can always add, subtract as many times 360 degrees as you like, okay? The other thing that we can do is take the magnitude on the left-hand side and the magnitude on the right-hand side. The magnitude on the left-hand side is given by the product of all the magnitudes of all the factors, magnitude of s minus z1 times s minus z2, blah, blah, over magnitude of s minus p1 times the magnitude of s minus p2, so on and so forth. This must be equal to the magnitude of the right-hand side. The magnitude of the right-hand side is 1 over k, regardless of the sign of k, okay? Good. Okay, so in an ideal world, this is all you need to know about the root locus, okay? Because really, in order to draw this root locus, you only need to know these two rules. But let's see what they actually mean more in practice, okay? So essentially, the idea here is the following. So I have my open loop transfer function, that has a number of poles, let's say this pole here, and this 0 here, okay? Then what I'm saying is that a certain point S in the complex plane, what I want to figure out is, so essentially root locus means what is the set of all points in the complex plane that could possibly be a closed loop pole for some choice of K, okay? So then I can ask this question. So is it possible to put a pole of the closed loop system at this location here? What I will have to do is, have to make sure that the sum of all the angles from the zeros to that particular point minus the sum of all the angles from each one of the poles to that particular point and from other, for all the poles from that particular point must be equal to 180 degrees plus or minus 360, or to 0 plus or minus 360, okay? If yes, then there will be one value of K such that the closed loop pole, one of the closed loop poles will be at that location. How can you compute that value of K? Use that magnitude condition, okay? Let's see what this all means in practice. First consequence of everything we said up to this point. All the points on the real axis to the left of an even number of poles or 0 are on the negative K root locus. Why is that? Let's say that we have a number of poles like that, okay? Would this point be on the root locus? What you have to do is compute what is the sum of all the angles from the zeros. Oh, let's put a 0 somewhere, okay? What is the angle from this 0 to this point? Is 0, right? Minus, what is the angle from this pole to that point? Again, it's 0. Okay? What is the angle from this pole to that point? Well, will be, say, 10 degrees, whatever, okay? But what is the angle from this pole to that point? This will be negative 10 degrees, okay? So you see that the sum of all those angles at this point is actually 0. So would this point be on the root locus for some value of K? Yes. Would this value of K be positive or negative? This is actually a negative K, negative gain root locus, okay? Same argument. So let's say that we start at this point, at the origin. What would be the angle from this 0? That's 0. What is the angle from this pole? Say 45 degrees. The angle from this pole is negative 45. So these two kind of cancel out, right? So this is, again, we are at net of 0. What is the angle from this pole? Is actually 180 degrees, okay? So what you see is that this point will actually be on the positive gain root locus, okay? You can summarize this from, by saying that all the points that are actually to the left of an odd number of poles and or zeros, these are actually on the positive gain root locus, which is also, typically when you talk about the root locus, you kind of implicitly say positive gain, okay? On the other hand, all these other points on the real axis will be on the root locus for negative K, okay? So first rule, all the points on the real axis can be a closed loop pole, either for positive K or for some negative K. First rule, okay? Let's talk about the breakaway or breaking points in a minute. What happens when K, we're talking about what happens when K goes to infinity, okay? And we have more open loop, so we know that if we have the same number of open loop zeros as the number of open loop poles, we know that the closed loop poles will move from the open loop poles to the open loop zeros, okay? What if you have more poles than zeros, okay? So then what we have to do is, what we say is that the closed loop poles will actually go to infinity, okay? Infinity on the complex plane may mean a lot of things, right? So essentially all points that are far away from the origin are at infinity. So really what we have to say is that we have to talk about infinity and what direction of infinity I'm choosing, okay? Again, we use the angle condition. The point here is that if we are zooming out sufficiently far, the contribution of all the poles will essentially be as if all the poles in zero were actually the origin, because we are looking from so far away that all the finite poles in zeros will essentially be the same as being at the origin. So the angle of all the terms of the numerator will be m times the angle of s, minus the sum of all the angles from the terms of the denominator will be just minus n times the angle of s, and this must be equal to the angle of either 0 or 180 degrees. Essentially what this means is that the asymptotes of this, the angles of these asymptotes will be given by this formula, okay? So either 0 divided, 360 degrees divided by n minus m, or 180 degrees divided by n minus m. This asymptote will actually meet at a point that you can think of it as a center of mass. It's a point that needs to lie on the real axis. This will be given by, think of it as a center of mass where the poles have unit mass and the zeros have negative unit mass, okay? We'll do examples, okay. Finally, we get to an example. Okay, so now what we have here is a first order system. You see that there's a first order system with an unstable pole, okay? So what would the behavior of this system look like? Open loop. We have an unstable pole, right? So then the response will be something like that. Clearly something that we don't like, okay? So now something that we can do is we can apply a feedback control, right? So we say that, okay, so now u is equal to minus kx or minus ky, right? And this is exactly what we get out of this feedback interconnection, okay? Now, what we know is, what we want to figure out, okay, so what happens to the pole of the system as I close the loop with this feedback gain? What we know is that, okay, for all the values, essentially the real axis will be on the root locus, right? So all the points on the real axis will be on the root locus. In particular, for k positive, the closed loop poles will be to the left of this, of my open loop pole, and it will be on the right of my open loop pole for k negative. Okay, you see that. Okay, so for k very small, so for k is equal to 0, my closed loop pole will actually be at the same point as the open loop pole, because essentially I'm not applying any feedback. So my closed loop behavior will really be the same as the open loop behavior, okay? As I increase the value of k, then what I know is that my closed loop poles will go towards the zeros, but I have no zeros in this case. So they don't have anywhere to go, so they will go to infinity. In which direction at infinity will they go? So essentially what I had to compute is 180 degrees divided by how many more poles than zeros I have. In this case, I have one more pole than zeros. So the asymptote will actually be at 180 degrees, okay? So what I know is that for k goes to plus infinity, then this will go to infinity with an angle of 180 degrees, meaning go to infinity to the left, okay? On the other hand, for k go to infinity, but with a negative absolute value, with a negative value, then what I will have is 360 degrees divided by 1, meaning 360 degrees, and then so essentially what I know is that as k goes to negative infinity, my closed loop pole will go to the right. What does this, okay, so this is the root locus for this particular case. What this is telling you is the following. Open loop is here, so my system is unstable. I start increasing k using positive numbers, and what happens is that initially I will move this closed loop poles a little bit to the left, a little bit to the left, a little bit to the left, right? So essentially, initially what I will be doing is I'm making it still unstable, but less so, right? So we'll blow up, but a little bit more gently, right? So for example, if the closed loop pole were here, this would be something like a slower exponential, okay? But then I can keep increasing the gain, right? And I put the gain here, right? I can put my closed loop pole here, and this would be now a decaying exponential. If I increase k, what do you think will happen? I will keep moving the closed loop poles to the left, meaning that my system will be stable, but also a faster response. Okay? Going back to the cabin example. Essentially, the more aggressive you are, right, in setting that the temperature control, the faster you will converge to your desired temperature. Okay? On the other hand, and again, this is another thing that I guarantee you that you will make this mistake at least once in your career. At some point, you are confident about, you're a great controls engineer, you're very confident, you do your thing in MATLAB or whatever. At some point in your life, you will get the sign wrong, okay? So now you are convinced, okay, so I choose my gain to be, say, +2, so that will place my closed loop pole, say here. Then you do your coding, and then you forget, you make a sign error. And now instead of having your gain at +2, you have your gain as -2. Essentially what happens is that if you're feeling too hot, you're actually increasing the setting on the heater, right? So actually what will happen is that you will be on this other side, and now instead of blowing up gently, will blow up, very aggressively, okay? So careful with signs, okay, when you're doing feedback. So, I actually keep in my lab all mementos of things that went wrong when people got careless, or have all these parts and pieces of destroyed destroyed cars or destroyed airplanes or things like that. Okay, I guarantee it will happen. Okay. Okay. Do you get the sense of okay? We will do more and more examples, but do you get a sense of what we are trying to do here? What we are trying to do here is to try to understand from the knowledge of the open loop behavior, just this pole here, what will happen if I apply feedback for different values of the feedback gain, okay? And what we found in this particular case is that as I increase k, I can make my system, the pole of my system, become stable, and I can make it as fast as I want in the stable region. Okay? Other examples. Okay, so now what I have is a system with these two poles. Okay? Again, for k is equal to 0, I know that my two closed loop poles will actually be exactly the same, at the same point as my open loop poles. What can I say about my the real axis? Well, what I know is that this part will be on the root locus for positive k. These parts will be on the root locus for negative k. Okay? Okay, so now what we have is the following. So as I increase k from 0 and I make it like a small positive value, remember that the closed loop, the number of closed loop poles must be exactly the same as the number of open loop poles. Okay, so I will have two closed loop poles. One will be here, one will be here. I keep increasing k, and these two poles get closer and closer and closer and closer. At some point, they get to coincide. What will happen is that they will actually break away from the real axis. Okay. what do they do? Okay, so now we look at the asymptotes. Okay, so now how many excess poles do we have? Now we have 2 excess poles. Where will the asymptotes be? So we know that we have 2 poles too many. These 2 poles will want to go to infinity. In what direction? For positive k, 180 degrees divided by 2, because that's the number of excess poles that we have. So this would be 90 degrees. Okay? So I know that actually 1 pole will go to infinity at plus 90 degrees. The other one will be the same. Everything must be symmetric up and down, okay? So then for k goes to plus infinity, what you will do is just go up here, and k goes to plus infinity, you go down here, okay? So the 2 poles for small values of k will start at the open loop poles. They will get closer, they will break away, go to infinity, up and down, okay? What happens for positive values of k? 1 asymptote, so now we have 360 degrees divided by 2. So what we get is 180 degrees, okay? So for k goes to negative infinity, you will go this way. For k goes to negative infinity, you will go this way. Okay? In particular, what you see from this plot is that if you have this system, can we actually stabilize it by a feedback gain? Is there a point on this root locus where both the poles are actually on the left half plane? Okay, so you see that no matter how big you make your control gain, your closed loop poles you will stay in the right half plane. The real part will be positive. Sorry. Well, you can say, well, I mean, let's use a negative gain, right? Because now we are here. Yeah. So 1 pole will be stable, but the other pole will be unstable. Okay? So this is a particular case of a system that no matter how hard you try, you can never find a feedback gain that will stabilize it. So you have to do something a little bit more sophisticated. There's another one. So now I have 2 poles that are actually complex conjugate and they're stable. Same as before. So now what we know is that the whole real axis is actually on the, it's actually the other way around. The whole real axis is actually on the negative gain root locus. Okay? What happens to the closed loop poles? So for k is equal to 0, they start at the open loop poles. As k gets larger, we know that they will never go to the real axis, right? But as k goes to infinity, where do they go? 180 divided by 2. So they go to plus 90 and negative 90. Okay, so I know that my poles will do something like that, okay? For negative value of k, actually what they will do is they will approach the real axis, meet somewhere here, and then one will go in this direction. So k goes to negative infinity, k goes to negative infinity, this is k goes to plus infinity, and this also k goes to plus infinity. You see? See what is happening? So now what you learn from this? So essentially, if you have this system and you apply feedback, what is happening to your response? It's not decaying faster, right? But it's actually oscillating more at a higher frequency. Okay? That's something that you may like or maybe you don't like. Okay? Other examples. Okay, so now we have a 0. First thing, I actually have, typically when I draw root locus, I have my steps, right? So the first step is, let's look at what happens on the real axis, right? So then what we know is that, okay, so this will be on the negative gain root locus. This part of the real axis will be on the positive gain root locus. How many asymptotes will I have? So I have 2 poles, 1, 0. 1 excess pole. In what direction will be that excess pole for positive k? 180 degrees divided by 1 is 180. So I know that for k goes to plus infinity, I have 1 pole that will go in this direction. Where does the other pole go? The other pole will go to the 0. Okay? Right? So we know that for k goes to infinity, one of the poles, so the poles will go either to the open loop zeros or to infinity to one of these asymptotes. In this case, in particular, what will happen is that I know that as I increase my k from 0, starting at the open loop poles, I know that eventually the closed loop poles must make their way to the real axis. Everything must be symmetric up and down, okay? So what they will do is actually something like that, okay? And then one of the poles will go to the 0, the other pole will go to the asymptotes at 180 degrees, okay?
What did you mean with the...
See, this is all the points that will be where the closed loop poles may be for some values of k, right? So we know that for k is equal to 0, one of the closed loop poles will be here, the other closed loop pole will be here, right? Then I know that for k very large, one of the poles will get to the 0, one of the poles will get to negative infinity on this side, right? Then I don't know exactly how they do it, okay? For that, you need MATLAB, okay? You want to use MATLAB. But what I know is that eventually, this part of the root locus, this part of the real axis is on the root locus for positive k, right? So I know that eventually, I will have my closed loop pole, say, 1 here and 1 here, right? Before we get there from k is equal to 0, essentially we need a way to get from this point to this part of the real axis, okay? Really, this is, and this is all you need to do. So this is the beauty of it, right? So in order to understand what will happen to my closed loop as I change k, I don't need to do complicated calculations. This is something that you can do in exactly 5 seconds, as I did here. Okay, maybe the first one will take you longer than 5 seconds, but eventually you will get to the point where you can do this sketch in 5 seconds, okay? So essentially what you see here is that as you increase k, what will happen is that your closed loop poles will go through some direction here, right? And in particular, what is happening is you can think of, typically what people like is, I noticed that on Piazza people were asking if you want critical damping. You don't want critical damping, typically. What you want is, you typically want your closed loop poles to be essentially at this 45-degree angle kind of thing, okay? Because critical damping is too slow. If you put these poles at that 45-degree angle, what it means is that actually you have a little bit of an overshoot, but then go quickly to the steady state value, okay? So in this case, you see that for some value of k, you will be actually able to put your closed loop poles around here, okay? If you want to dampen them more, fine, you can dampen them more, right? But then eventually this will be, just 2 real exponential if you want, okay? The point of the root locus is, for me, is not to give you detailed, precise answers. The point of the root locus is to see whether or not a certain design may actually work, okay? And in this case, you know that this is a system that I can stabilize and get to a nice response just by using proportional feedback, just using a feedback gain, okay? Again, the point of the root locus is to give you the 5-second answer to the question, what is the right control architecture for this system? Okay? And another one here. Okay, so, yep. Oh, yeah, great point. I know that for k goes to negative infinity, one of the poles will go here, right? Will go to the 0, right? Coming from the other direction. The other pole will go to infinity. What is infinity in this case? This will be 360 degrees divided by 1, which is 0, okay? So what you will see is that eventually one of the poles will have to go here, one of the poles will have to go here, right? And they're starting here, right? So what will happen is that these two poles will get closer to the real axis, meet up somewhere here, and then one will go to the 0, one will go to plus infinity, okay? Another example. Okay, so this is on the negative gain root locus. This is on the positive gain root locus. What are the asymptotes in this case? Now we have 3 poles, no zeros. So I have 180 degrees divided by 60. 180 degrees divided by 3, which is 60 degrees. So what will happen is that I have these asymptotes this way. Okay, by 60 degrees, okay, and minus 60, clearly. So one of them will go to, and the other one will be, you can think of, is 180 degrees divided by 3, but you can also think of 180 degrees plus 360 degrees divided by 3, which means 60 degrees plus 120, which gives you this asymptote here. Just maybe for a second, because it's something important here. So what will happen here is that the root locus will look something like that, okay? What you're seeing from here, and again, this is why it's important to do root locus, what you see here is that, yes, the system is stable, okay? By using feedback, you can change the closed loop poles, right? And maybe put them somewhere you want. However, you have to be careful, because there is some value of k such that if you exceed that value of k, if you use a k that is too large, what happens to your closed loop? It becomes unstable, okay? And this is what happens when people started designing, for example, controllers for helicopters. Helicopters has to happen, has to be like happens to be a third order system. If you crank up your gain too much, then you think that you're making the system more stable. No, 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 you're actually making it unstable. Okay? And again, this is another example where you see that just by sketching this 5-second root locus, you can understand some of these properties. In this particular case, using too large of a gain will actually give you instability. Okay? Okay, fine. We'll do more examples in exercises and next time. Thank you. Oh, by the way, next week I had to be in Singapore for some business there. Jacopo Tani, one of my Ober assistants, will give the lecture.